Welcome! In this session, we'll explore LeetCode problem number 971, flip binary tree to match preorder traversal. We'll break down the problem, analyze the algorithm, and walk through the solution step by step. Let's dive right in. In this problem, you are given the root of a binary tree with n nodes, where each node has a unique value ranging from 1 to n. Additionally, you are provided with an array called voyage, which specifies the desired preorder traversal of the binary tree. The goal is to determine whether you can modify the tree to match this preorder traversal. To achieve this, you are allowed to perform a specific operation called a flip, where you swap the left and right children of a node. The task is to return a list of the node values that need to be flipped, in the order they are flipped, to match the voyage. If it's not possible to achieve the desired traversal, you should return -1. The input consists of the binary tree represented as a tree node object and the voyage array. The output is either the list of flipped nodes or -1 if the voyage is impossible to match. To clarify further, the tree node structure used to represent the binary tree is defined in Python code. Each tree node object has three attributes: val, which stores the node value, and left and right, which refer to the left and right children of the node, respectively. Now, let's look at some examples to understand the problem better. In the first example, the tree has a root node with value 1 and a left child with value 2, while the voyage is 2, 1. Here, the root node's value does not match the first value in the voyage, making it impossible to achieve the desired traversal. As a result, the output is -1. In the second example, the binary tree has three nodes, the root with value 1, and two children with values 2 and 3. The voyage is 1, 3, 2. The root node's value matches the first value in the voyage, but the left child is 2, while the voyage specifies 3 as the next value. To resolve this, we flip the left and right children of the root node. After the flip, the tree becomes 1, 3, 2, which matches the desired preorder traversal. Since we flip the root node, the output is 1. Here, the explanation continues for the second example. After flipping the root node, the updated tree perfectly matches the voyage. Since the root node was flipped, we return 1 as the output. In the third example, the tree again has three nodes, with the root value of 1 and children 2 and 3. The voyage is 1, 2, 3, which already matches the tree's preorder traversal. Since no flips are required, the output is an empty list, indicating that the tree already satisfies the given voyage. Now, let's consider some additional details and edge cases. The voyage array is always a permutation of the integers from 1 to n. For an empty tree with an empty voyage, the output is an empty list because the tree trivially matches the voyage. In a tree with only a root node, such as 1, and a voyage of 1, the output is also an empty list because a single node always matches its voyage. When the root value does not match the first value in the voyage, such as in the input 1, 2, and voyage 2, 1, it's impossible to achieve the desired traversal, so the output is -1. Finally, there are cases where multiple flips are necessary. For example, in a tree with nodes 1, 2, 3, 4, 5, and a voyage of 1, 3, 2, 5, 4, we need to flip the root node first to make 3 the left child. Then, we flip node 2 to make 5 its left child. These flips ensure the tree matches the voyage, and the output is 1, 2, representing the nodes flipped in the order they were flipped. This example highlights how the problem can involve multiple steps to achieve the desired traversal. To solve the problem of flipping a binary tree to match preorder traversal, our goal is to ensure that the tree's traversal aligns exactly with the given voyage array. If this is not possible, we return -1. Otherwise, we need to return a list of node values where flips occurred. To achieve this, we must carefully simulate the preorder traversal while dynamically flipping nodes as needed. Let's consider the approaches. First, the brute force approach. The idea here is to try every possible combination of flipping left and right children at each node to see if the resulting preorder matches the voyage. However, this approach is computationally infeasible. Since each node can have two children, the number of combinations grows exponentially, leading to a time complexity of 2 to the power of n. This makes it impractical for larger trees. It also doesn't take advantage of the tree structure or the constraints of the voyage. On the other hand, the greedy preorder traversal with flipping offers a more strategic approach. Here, we traverse the tree in preorder while directly comparing node values to the voyage. If we encounter a mismatch that requires flipping, we swap the left and right children and continue. This minimizes unnecessary operations by flipping only when absolutely required. This greedy approach is efficient because we visit each node exactly once, resulting in a time complexity of O(n), where n is the number of nodes in the tree. The space complexity is O(h), where h is the height of the tree, due to the recursion stack. However, it does assume that the voyage represents a valid preorder traversal of the tree. Another possible method is the iterative preorder traversal. Instead of recursion, we use a stack to simulate the traversal. At each step, we compare the current node's value to the voyage and decide whether flipping is needed. This approach avoids the recursion stack, potentially saving space for very deep trees. However, managing the stack manually can make the implementation more complex and error-prone. After evaluating these methods, the greedy recursive approach was chosen. It is simple to implement, aligns well with the tree's structure, and directly meets the problem's requirements with an optimal time complexity of O(n). Its recursive nature also makes the code easier to understand, as it naturally mirrors the preorder traversal process. Now, let's focus on the key observations that make this approach effective. Preorder traversal follows the sequence: root, left subtree, right subtree. If the voyage demands a different order, such as visiting the right child before the left child, flipping becomes necessary. However, if at any point the voyage specifies an order that is impossible to achieve, for example, due to mismatched values, we can immediately return -1 and terminate further computations. This helps in pruning unnecessary operations early. The chosen approach works because it is efficient, with O(n) time complexity ensuring scalability for large trees. It is also clear and intuitive, as the recursive structure naturally mirrors the traversal process. Additionally, the ability to dynamically flip nodes as needed makes it flexible for handling any valid voyage. While iterative traversal could save recursion overhead, the added complexity of managing the stack manually makes it less appealing. Similarly, the brute force approach, with its exponential time complexity, is impractical for large inputs. By focusing on efficiency and clarity, the greedy traversal proves to be the most effective solution for this problem. In this problem, we need to determine if we can make the preorder traversal of a binary tree match a given voyage array by flipping certain nodes. Recall that a preorder traversal visits the root first, then the left child, followed by the right child. Flipping a node means swapping its left and right children. If it's impossible to match the traversal to the voyage, we return -1. Otherwise, we return a list of node values where flips occurred. To approach this, we first define a result list to store flipped nodes and an index pointer to track our position in the voyage. Then, we use a recursive depth-first search, starting from the root, and check if the node values align with the voyage. Any mismatch means an immediate return of -1. This keeps the algorithm efficient and focused on matching the traversal step by step. Now, during the depth-first search, if the current node value doesn't match voyage index, we know there's no valid solution, so we return -1. Otherwise, we increment the index pointer to move to the next value in the voyage. Next, we check the children of the node. If the left child matches the next value, we recursively traverse the left subtree first, then the right. However, if the right child matches the next value but the left child doesn't, we record a flip by adding the node value to the result list. We then prioritize the right subtree first, followed by the left. If neither child matches, we return -1, since it's impossible to align the traversal. The traversal ends successfully if we process all nodes without mismatches, and in that case, we return the result list. Otherwise, any mismatch at any stage results in -1. Additionally, let's consider edge cases. For instance, if the tree is empty, meaning root is null, the output should be an empty result list, as there are no nodes to flip. If the voyage array is shorter than the number of nodes in the tree, it's impossible to match the traversal, so we return -1. Similarly, any mismatch during the traversal leads to an immediate return of -1. To implement this efficiently, we use specific data structures, a result list to store flipped nodes, a single pointer index to avoid slicing the voyage array, and the recursive call stack for depth-first traversal. The pseudocode demonstrates how this works step by step, starting with a base case where an empty node returns true. If the node value doesn't match voyage index, we return false immediately. Otherwise, we increment our index and proceed to check the children. If the left child matches the next value in voyage, we recursively traverse the left subtree, followed by the right. If the right child matches instead, we record the current node as a flip by appending its value to the result list. Then, we traverse the right subtree first, followed by the left. If neither child matches the next value in voyage, we check if both children are null, which would indicate a leaf node. If the recursive depth-first search completes successfully, we return the result list containing all flipped nodes. Otherwise, any mismatch along the way causes the function to return -1. This structured approach ensures that we only perform the necessary flips and terminate early if the traversal cannot align with the voyage. By directly comparing node values with voyage index, we minimize unnecessary computation and keep the algorithm efficient. To analyze the complexity, the time complexity is O(n), where n is the number of nodes in the tree. This is because each node is visited exactly once during the traversal. The space complexity is O(h), where h is the height of the binary tree, as this accounts for the recursive call stack. Key operations include comparing the node value with voyage index to ensure alignment and incrementing the index pointer to progress through the voyage. By recording flips only when necessary, we minimize operations and avoid redundant checks. Early termination on mismatches further optimizes the algorithm by stopping unnecessary work. Using a single pointer to track voyage instead of slicing subarrays also enhances efficiency. Overall, the greedy approach ensures we perform the minimal number of flips required to match the voyage, making this solution both effective and computationally optimal. This implementation solves the problem using a depth-first search (DFS) approach to traverse the binary tree while comparing it to the given voyage array. The flipMatchVoyage function initializes a result list to track nodes where child flips occur. It also sets an index to track the current position in the voyage array. The inner helper function DFS performs the traversal. It first checks if the current node is null, returning true if so, as there's no mismatch possible. If the node's value does not match the current voyage index, the function immediately returns false. Otherwise, the index is increment to move to the next value. If the left child exists and its value does not match the next value in the voyage, a flip is required. The current node's value is added to the result list, and the function recurses first on the right child, flipped, and then on the left child. If no flip is needed, the function proceeds with normal preorder traversal by recursing on the left and right children. Finally, the function returns the result list if the traversal succeeds. Otherwise, it returns -1 to indicate that matching the voyage is impossible. This solution efficiently handles the problem with a time complexity of O(n), where n is the number of nodes in the tree, as each node is visited exactly once during the traversal. Here, we begin by defining our Java solution for the problem. First, we declare the class solution and initialize a private variable index to 0. This variable will keep track of our current position as we traverse the voyage array. The main method, flipMatchVoyage, accepts the root of the binary tree in the voyage array as inputs. It returns a list of integers, representing the nodes that need to be flipped to match the preorder traversal defined by the voyage. If the tree cannot be flipped to match the voyage, the method will return a list containing only -1. Inside this method, we call a helper function, DFS, which performs a depth-first search on the tree. The DFS function is the core of our implementation. If it fails to reconcile the tree structure with the voyage, we return -1, otherwise, we return the list of flipped nodes. The DFS function starts by ensuring that null nodes are valid and immediately returns true for them. Then, it checks if the current node's value matches the expected value in the voyage array. If not, the function returns false, indicating that the tree cannot be adjusted to match the voyage. If the values match, we increment the index to move to the next position in the voyage array and proceed to check the children of the current node. Now, the DFS method evaluates whether a flip is required. This happens when the left child exists but does not match the next value in the voyage array. In this case, we record the value of the current node in the result list, as this node represents the root of a subtree where the flip occurs. Then, we recursively call DFS on the right child first, followed by the left child, effectively flipping the traversal order for this subtree. On the other hand, if no flip is needed, we simply perform a normal preorder traversal, recursively visiting the left child first and then the right child. The method ensures that the traversal adheres to the voyage array by validating each node's value at every step. Finally, we define the structure of a binary tree node within the treeNode class. Each node has an integer value and pointers to its left and right children. This structure allows us to represent the binary tree and traverse it as required by the problem constraints. Here, we start with the first example where the binary tree matches the preorder traversal without requiring any flips. The tree has a root node with value 1, a left child with value 2, and a right child with value 3. The voyage provided is 1, 2, 3, so we begin by checking the root. The value of the root node matches the first value in the voyage. We then increment the index in our voyage to move forward. Next, we move to the left child of the root, which has value 2. Again, this matches the current value in the voyage, so we increment the index again. Since the left child of node 2 is null, we return true and do the same for the right child of node 2, which is also null. This confirms that both left and right subtrees of node 2 are valid. Finally, we move to the right child of the root, which has value 3. This matches the next value in the voyage, so we increment the index once more, completing the traversal of this node. Now, we check the left and right children of node 3, which are both null. Since we've reached null nodes, we return true for both sides, confirming that the left and right subtrees of node 3 are valid. With this, the entire tree matches the voyage perfectly without requiring any flips. The result is an empty list, indicating no flips are necessary. Moving to the second example, the tree remains the same as before, but the voyage is now 1, 3, 2. This new voyage introduces a mismatch that will require a flip. We begin by checking the root node, which has value 1. This matches the first value in the voyage, so we increment the index to proceed. Next, we move to the left child of the root, which has value 2. However, the current value in the voyage is 3, not 2, indicating a mismatch. To resolve this, we flip the left and right children of the root. We record this flip by adding the root's value, 1, to our result list. After flipping, we move to the new left child, which is now node 3. This matches the current value in the voyage, so we increment the index again. Checking the left and right children of node 3, which are both null, we return true for both. Then, we move back to the new right child, which is node 2. This matches the next value in the voyage, so we increment the index once more. Finally, we check the left and right children of node 2, which are both null, returning true for both. With this, the entire tree matches the voyage, and the result is 1, indicating one flip at the root. In the third example, the tree has a root node with value 1, a left child with value 2, and no right child. The voyage provided is 1, 3. Starting at the root, the value matches the first value in the voyage, so we increment the index. Next, we move to the left child of the root, which has value 2. However, the current value in the voyage is 3, not 2, resulting in a mismatch. Since the right child of the root is null, a flip is not possible. At this point, we immediately return false because the voyage cannot be matched to the tree structure. The output is -1, indicating that it is impossible to match the voyage. To summarize, example 1 demonstrates a perfect match between the tree and the voyage, requiring no flips. Example 2 shows how a mismatch between the left child and the voyage can be resolved by flipping the left and right children of the root, resulting in one flip. Example 3 illustrates a case where the voyage cannot be matched due to a fundamental structural mismatch. The algorithm uses depth-first search to traverse the tree, comparing each node's value with the voyage and flipping when necessary. The result list records the nodes where flips occur, while -1 is returned if the voyage cannot be matched. The time complexity of this algorithm is O(n), where n is the total number of nodes in the binary tree. This is because the algorithm performs a depth-first traversal, or DFS, which ensures that each node is visited exactly once. Let's break this down further. During the recursive DFS traversal, each node is processed individually. For every node, we perform constant-time operations like comparing the node's value to the corresponding value in the voyage list and determining whether or not a flip is needed. These operations take O(1) time per node, so when we multiply this by the total number of nodes, we get an overall time complexity of O(n). Additionally, if a flip is required for a node, it is recorded in the result list, with the operation of appending to the list also running in constant time. Since the total number of flips is at most n1 for each node, this step doesn't significantly impact the overall complexity, keeping it firmly within O(n). Now let's analyze the best, average, and worst-case scenarios for time complexity. In the best case, the voyage matches the tree's natural preorder traversal, meaning no flips are required. However, the DFS still visits every node, so the time complexity remains O(n). In the worst case, every node in the tree requires a flip, but even then, the algorithm still only visits each node once, making the complexity O(n). On average, the algorithm processes each node once and performs constant time operations per node, so the time complexity remains consistent at O(n). Next, let's discuss space complexity. The algorithm has a space complexity of O(h), where h is the height of the binary tree. This is due to the recursive DFS traversal, which uses the function call stack to store information about the current path of traversal. The height of the tree determines the maximum depth of the recursive stack. For a balanced binary tree, the height is O log n, while for a skewed tree, the height can be as large as O(n). In the worst case of a completely unbalanced tree, the space usage will reach O(n). Continuing with the space complexity, we also need to consider the result list. This list stores the values of nodes where flips occur. In the worst case, every node may require a flip, so the result list could grow to size n. However, this additional memory usage is separate from the recursive stack. The voyage list, on the other hand, is provided as input and does not contribute to additional space usage. Similarly, the index variable, which keeps track of our position in the voyage list, is just a single integer and takes O(1) space. Bringing these components together, the final space complexity depends primarily on the recursive call stack. For a balanced tree, where the height is O log n, the space complexity is O log n. For a skewed tree, where the height is O(n), the space complexity is O(n). On average, for a typical tree, the height is closer to O log n, so the space complexity in most cases would be O log n. Let's compare this optimal approach to a brute force or naive approach. A naive solution would involve generating all possible permutations of the tree by flipping nodes and then checking each permutation against the voyage. This would result in an exponential time complexity of O(2 to the power of n), as there are 2 to the power of n possible ways to flip the nodes of a binary tree with n nodes. Additionally, the space complexity would also be much higher due to the need to store intermediate tree states. In contrast, the optimal algorithm avoids this inefficiency by directly simulating the preorder traversal and making decisions in real time, such as flipping children only when necessary. This reduces the time complexity to O(n) and the space complexity to O(h). Mathematically, for time complexity, each node is visited exactly once, and each operation per node is O(1), which together results in O(n). For space complexity, the maximum depth of recursion corresponds to the height of the tree, leading to a space complexity of O(h). Common mistakes in this problem often stem from misunderstanding key constraints. For instance, attempting to flip a node without verifying if its children can satisfy the voyage order is a critical error. Flipping should only happen when it helps align the left and right children with the expected sequence, otherwise, it leads to incorrect results. Another frequent mistake is failing to handle mismatches early. If you encounter a node whose value doesn't match the current position in voyage, the output is guaranteed to be -1, so there's no point in continuing. This is why early termination saves both time and unnecessary computations. Additionally, an improperly updated index pointer can throw off the entire traversal. The algorithm hinges on accurately tracking the current position in voyage, and missing updates can lead to misalignment and ultimately, incorrect results. Handling null nodes is another potential pitfall. Null nodes don't physically exist in the tree, and they shouldn't appear in Voyage. Attempting to process null children as if they were valid nodes will likely cause runtime errors. Similarly, choosing an inefficient traversal strategy can doom your solution. This problem explicitly requires preorder traversal. If you use postorder or level order traversal instead, you'll fail to match the Voyage sequence. Preorder traversal is fundamental here because it ensures nodes are visited in the exact order specified by Voyage, which is the key to solving this problem. This problem is a great test of your understanding of tree traversal and recursion. In an interview, you should be ready to explain how preorder traversal works and why flipping nodes is necessary under specific conditions. Be prepared to discuss edge cases, such as a tree with only one node, scenarios where flipping is either required or impossible, and examples of completely unbalanced trees. Optimization is another critical focus area. Highlight the importance of making decisions, like flipping, locally and terminating early when mismatches occur. Finally, communication is key. Clearly explain how you ensure the Voyage order is respected at each step, and use examples to demonstrate how flipping aligns the structure with the preorder sequence. This problem connects to several other tree-related problems on LeetCode. For example, LeetCode number 144, Binary Tree Preorder Traversal, focuses on the basics of preorder traversal, which is fundamental here. LeetCode number 226, Invert Binary Tree, involves flipping nodes and shares some conceptual similarities. LeetCode number 199, Binary Tree Right-Side View, is another traversal problem but with specific output conditions. Lastly, LeetCode number 1372, Longest Zigzag Path in a Binary Tree, also explores traversal under constraints. For alternative approaches, a greedy strategy with early termination can be effective. You traverse the tree in preorder, comparing nodes with Voyage and terminating immediately if there's a mismatch. This approach is highly efficient, running in O(n), but requires careful handling of edge cases like null nodes. Another option is an iterative approach using a stack to simulate preorder traversal. While it achieves the same result, it's more complex to implement and uses more memory compared to recursion. Backtracking is another approach worth discussing, particularly for its thoroughness. Using backtracking, you can explore all possible combinations of flips to match the Voyage. While this guarantees correctness, it comes at a significant computational cost. In the worst case, backtracking can have exponential time complexity, which makes it impractical for larger trees. However, it's a useful approach to understand when considering all possible solutions to the problem. Great job! We've summarized key insights from solving the problem. Remember to practice similar problems to reinforce your understanding. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!